Hey, feeling good, like I should. When in dark, I walk around the neighborhood, feeling blessed.
Alrighty, let's take a look at our homework. So we're going to start off with the whole idea of combining like terms. The algebra tiles are wonderful tools for us to help us understand what we do and why we do it when we are combining like terms. So the like terms are the terms that have the same variable raised to the same power. And so you may not realize this, but every single number, every single variable has an exponent. So if we take a look, we see that's x squared, right? Here there's no exponent, but it's understood to be x to the first power. But when we don't have an exponent, it's just, that's understood, okay? Just like this is 1x squared, we're not going to necessarily write the 1 to the left of the x squared to say there's 1x squared. We just know there's a 1 there, and I sometimes call that ninja 1. Just like here, 2 to the, if it's 2, it's 2 to the first power, right? But this could also be 2x to the 0 power, which we're going to learn in 8th grade what it means to have a 0 for an exponent. But technically, anything to the 0 power is equal to 1. 2 times 1 is equal to 2. So we don't need to worry about having that x to the 0 power there, and we don't need to worry about having that exponent for the x term. If it's more than x to the first power, we're going to put the exponent there. Otherwise, we'll just leave it blank. So how many total x squareds are there? Well, there's only one of them, right? So there's nothing to combine this guy with. There's your x squared. How many x terms are there? There's 2 of them. So we're going to call that 2x's. And then how many ones are there? There's 2 of them. So we're going to call that the number 2. Since we know 2 times 1 is equal to 2, we can actually simplify that one. So the like terms are always the terms that have the exact same variable raised to the exact same power, okay? So if you take these 2 terms and you combine them, 2x squared and negative 5x squared, you're going to take the 2 and the negative 5 and you're going to add them together. And so the total sum of those 2 becomes negative 3x squared. And here you got 4 ABs and 3 ABs to make a total of 7 ABs. Okay. Now, if you were trying to add 5 and 3x together, you can't. So all you could say was 5 plus 3x because they do not have the same variable raised to the same power, so they cannot be combined. And this is where, oops, what is that right there? Oh, that's something on my screen. This is where using the algebra tiles helps you understand what the difference is between 3x's and 5 1s. If you put them all together, you don't have new tiles being created from that. So all you can do is keep them, in their own respective piles. 3x's here, 5 1s there. They cannot be combined, whereas these guys can be combined. Or these guys, you take your 4 from that pile and your 3 from that pile, shove them together, and you got a pile of 7 ABs. Now, what are ABs? What do they look like? I don't know. But, the fact is, AB is its own kind of variable term, just like x squared is its own variable term. Anything else to say here? All right, so this is typically what I would do if I was using my, my magic tools up here. I would take all my x squareds and highlight them. I would take all my x's and highlight them, and then take all my 1s and highlight them, and then combine the like terms. 2x squared and 1x squared makes 3x squareds. 1x plus 5x's makes 6x's, and then 3 plus 2 equals 5. So this would be the simplest version of this. So notice how we had 1, 2, 3, 4, 5, 6 different terms in this expression. Well, it's simplified when you have the fewest number of terms you can possibly get, and so 3 is the fewest we can get here. Now, if you do not have access to highlighters, and you want to use a different method, this is what I did when I was in high school. Sorry, hold on for a second. I've got a cat that's trying to walk around here. I'm going to have to pause for a moment so the cat can get past me. And being the little brat that he is, I just paused and he decided he didn't need to go anywhere, so now he's not moving, so I'm going to ignore him. All right, so this is what I would have done in high school. I would have drawn a circle around all the x squareds. And make sure that minus sign, we'll get to this a little bit later, instead of subtracting 2x squared, if you think of that as plus a negative 2x squared, that minus sign becomes the negative sign for the 2. And then that's it for the x squared terms. And now I'll maybe draw a rectangle or a square around all my x terms. And same thing applies here. That's minus x. So that would be the same as plus a negative x. So that negative is attached to the x. And then I'll leave the these guys just open. So what do we have? 3x squareds and a negative 2x squared. So what is 3 minus 2? That is 1x squared right there. So I'm going to cross these guys out because I've already combined them. And my 2x's and a negative 1, so 2 minus 1 is 1. So this is going to be my x term. And then 7 and 7 make 14. And so we end up with x squared plus x plus 14 as our simplified expression for this more complicated expression. All right, so let's go ahead and take a look at these. If we are going to find the perimeter of each shape, pretty straightforward, right? 1x here, a 1, 1, and a 1. Here's another x, here's another x, here's another x, and another 1. So a total of 4 x's and 4 1s. Here we got 1, 1, x, 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 1, 1, x. So this is also 4x plus 4. Now, do these two have the same exact area? They don't. The area of this one was x squared plus x plus 1, whereas the area for this one was x squared plus 2x. Not the same thing. So you can have two different shapes with different areas that have the same perimeter. What'll be interesting is if you've got two different shapes with the same area, if they'll always have the same perimeter as well. Something to explore. All right, figure A and B at the right are similar, which means that there is a common scale factor that you would multiply times one side to get its corresponding side. So what is that number? So if you take your 15 and your 3, those are the known sides, right? Those two sides are in the same exact location, given the two similar figures. So this is where we're going to find our scale factor. Now, I would say your scale factor, if you're going in this direction, would be times 5, right? And if you're going in the opposite direction, it would be divided by 5, which means the same as times 1/5. Now, if they say that you're going from figure A, with the original figure, to figure B, you would choose the scale factor that makes the number smaller. So when you multiply a number times 5, it gets bigger. When you multiply a number times 1/5, it gets smaller. And so that would be the appropriate scale factor to use in that situation. And there is a formula for scale factor. Remember, you take the original, everything is always based on the original, and so the 15 would go on the bottom because A is the original figure and B is the copy. So the new figure, or the copy, goes in the numerator, and that would be the 3. So you simplify it, and there you go. There's your scale factor, which is 1/5. But I tell students all the time, don't worry about which one is the original and which one is the new. Just take your known side lengths. Your scale factor is either going to be 5/1 or 1/5, depending on which direction you're going in. Okay, so notice that these two are reciprocals of each other. That's what happens, right? So 20 times 1/5 is 4, and 4 times 5 is 20. 18 times 1/5 ends up being 18/5, which is the same as 3 3/5, which is the decimal 3.6. So if you took 3.6 and multiplied it times 5, you would get 18 for an answer. And same thing here, 12 divided by 5 is 2 4/10, and 2 4/10 times 5 is 12. So a lot of times you'll have like a missing quantity here and a missing quantity there, and you've got to choose whether you're going to multiply or divide by your scale factor. I just think it's easier to go and multiply in either direction and just be aware of which scale factor you're going to use. Is it getting bigger? Then use a scale factor that's greater than 1. Is it getting smaller? Then use the scale factor that is less than 1. All right, I put in this clock here to help us with this process, okay? So it says, what fraction of 1 hour is represented by the following numbers of minutes? So 10 minutes technically is 10 minutes out of the 60 minutes, which is 1/6, right? And so I use the clock to say, all right, if it is 10 minutes, then that would be like this wedge right there, which would represent 1/6 of the total, right? This represents 1/6. The 10 minutes is 1/6. So you can use a visual there to help you. 15 minutes, that would be a quarter, right? That's a quarter of that entire thing because 15 out of 60 simplifies down to 1/4. Then 30 minutes, we know that's a half of an hour. And 20 minutes, that would be to right here. This section right there represents 1/3 of the entire clock. So 20 out of 60 is the same as 2 out of 6 or 1 out of 3. All right, Rayner bought 1.43 pounds of lunch meat at a store for $10.98. What is the unit rate? Okay, so we know this is proportional because if you buy no pounds of meat, you spend no money, and the fact that there's a unit rate means that there's a constant price per pound that you're going to be paying. So what is the unit rate in price per pound? Well, how do we do unit rate? We just take and write the rate as it's presented in the problem and then do the division problem. So if we take $10.98 and we divide it by 1.43 pounds, you're going to get this, which rounds up to 7.68, $7.68 per pound. Okay, and why are we taking $10.98 and dividing it by 1.43? Because if we're going to use our giant 1 here, we've got to figure out what do you divide 1.43 by to get 1 for an answer. And so the answer is you divide it by itself. Anytime you divide a number by itself, you always get 1 for an answer. So we have to create a giant 1 here. We have to divide the 10.98 by 1.43 as well. So after doing this kind of problem a few times, we start to realize anytime we're taking a unit rate, we're just taking these numbers and doing the division. All right, absolute value. When you find the absolute value of an expression, you're just taking its positive value, okay? So an elevation is 250 feet. Well, feet, there's no such thing as a negative foot, right? You take out your measuring tape or your yardstick, there's no negative signs on it. 250 feet is 250 feet, whether you're going up or you're going down. So the absolute value would be 250 feet. A credit card balance of $23.75, technically, actually, the more I think about that, that's probably a negative, right? Because you owe money if it's your credit card balance. So you don't pay money in negative amounts, so it's just you owe $23.75. The negative just is implying that it's money you owe, not money that you currently have. And then a football player rushes for -5 yards. That means he goes backwards. So if it was 1st and 10, now it's 2nd and 15, right? Because you lost 5 yards. So the absolute value is 5 yards. That's how much money there. That's how many yards you lost. And then your bank balance, this is a positive. $198.32 in your bank. Well, that's real money that is yours. So, you know, the absolute value of it is at $198.32. And then an elevation at Death Valley. I don't know if you recall this, but Death Valley is actually below sea level. Luckily, we've got those mountains on the coast that keep the ocean from flooding it. But distance is never really expressed as a negative. This just implies that this is how far below sea level it goes, which is 86 meters. But we'll put a negative sign in front of that just to depict that relative to sea level, this is you're going down instead of going up. And that's it for our homework. Hooray. All right, so let's move on to the next activity. Take care. Bye.
Hey, feeling good, like I should.